So it's a real pleasure for me to introduce today's speaker. His name is Xavier Fernández Busquets. He trained as a biologist at the Autonomous University of Barcelona, and then he did also his PhD there in the field of molecular biology. And then he went to do several postdocs, one in Switzerland, the Novartis in Basel, in Switzerland, and then he moved to the States, to the what's Marine Biology Institute, a nice place to work. Yeah, it's very in Massachusetts, close to the sea and so on. So very nice. And then he went back to Barcelona that was in 1999, and then after a few years he got one of these Ramon y Cajal contracts, and after that he started he got a position at the Institute of Bioengineering of Catalonia, IBEC, and later he became the head of Nano-Malaria Joint Unit, which is a joint unit between this Institute of Nanotechnology and the ES Global, which is an organization that's focused on malaria. Actually, today we were supposed to have two speakers, but one is actually in Africa, in Mozambique, and he couldn't come today, but Xavier, he will actually speak a little longer, and he's going to talk about nanotechnology against malaria. Thank you for coming, and we look forward for your talk.
Thank you, Pablo, for this nice introduction. So, as Pablo said, we belong to an institute that is a nanotechnology institute, which is IBEC. And then we are also affiliated to IS Global, because the things that we are doing are related to the application of nanomedicine or nanotechnology, in this case to malaria, although we are also expanding our activities to other infectious diseases like leishmania and others probably in the future, which we are planning. But what I am going to present to you today is focused on our work on malaria. I am not an immunologist, that's why I insisted that if you want something related to immunology, you will not get it from me. But there are a couple of experiments or things that I am going to explain that I think can be applied in general terms to vaccines, and in particular to malaria, because as you know, so far we don't have any good vaccine against any parasitic disease. These are very tricky organisms. In the case of Plasmodium, the malaria parasite, it's a protease that is constantly changing the proteins that it's exposing to the environment. That's why it's quite complicated to target an antigen against which you can make a vaccine. In addition to that, it has another series of clever strategies to escape immune surveillance and drugs and everything we throw at it. And this makes it a very challenging organism to develop vaccines against it. I am not working on that, but the people next door to my office are the ones who are doing the clinical assays for the RTSS vaccine. So some things I heard, and more or less I could understand what are the problems behind it. So briefly, as you know, Plasmodium, the causing agent of malaria, is a parasite that in the human infects red blood cells mainly. There is also a brief or not so brief, depending on the species, stage in the liver, but all the pathologic all the bad things that the people feel when they are infected come from the blood stages. Then because all the pathology from malaria comes from red blood cell infection, essentially all therapeutic issues have been directed at them. And there is where we started. As you will see, what I'm going to explain is our progress from our beginnings in trying to design or to improve the activity of anti-malarial drugs through targeted drug delivery strategies. And then we have been advancing towards trying to improve these strategies. And as you will see, we are currently planning to target other stages that are not in the red blood cell. What you see on the lower right is a distorted map of the world, which is, as you can see, not based on square kilometers, but in the number of malaria-related deaths. And then, as you can see, malaria is a problem for poor areas of the planet, essentially Africa, also Southeast Asia, and then also everything we are going to talk will have in the background this idea that if we develop nanomedicines, this is fine. Nanomedicines are very good alternatives, and some of them are already being used for diseases like cancer, neurological disorders, diabetes, which are pathologies of people in developed countries. But then there is still the misconception that nanomedicine is too expensive to be used in diseases that are prevalent in developing countries, like in this case Africa. Then a little bit I will try to demonstrate that this is not completely true and that we can always find new nanomedicines that are cost effective and that can be produced at an affordable price for using in Africa. Let me briefly outline the life cycle of the malaria parasite. If we start with a mosquito bite, it's the female that when it takes blood to develop her eggs, it injects from the salivary glands a form of the parasite, which is the sporozoite, and in a matter of minutes, because the malaria parasite in all its stages is a very fragile cell, and then it cannot survive outside of another cell for more than 3, 4, 5 minutes. Then, after this brief time, it has to infect an hepatocyte, and then it will experience a dormant stage in the liver that can go from hours to days to weeks to years, depending on the species. Eventually, it invades the blood circulation, and this is the erythrocytic cycle that I mentioned before. All the pathological effects of malaria come from red blood cell infection. Discomfort, nauseas, headaches, general health problems, they are all derived, also anemia, they are all derived from the infection of red blood cells, which can eventually end up in the most severe malaria cases, which are, for instance, cerebral malaria, which can lead to death. Eventually, some of the red blood cell infecting stages develop into gametocytes, which can only proceed with their development if they are taken up by a mosquito. Then when another mosquito bites the person, if it ingests gametocytes, those will develop in the mosquito midgut into, they will form the gametes, and after fecundation there will be a zygote, and this zygote will cross, after being transformed in a motile form, the ookinete, it will cross the midgut epithelium and form an oocyst, where sporozoites will develop, which will migrate to the salivary glands of the mosquito to start the cycle in the next mosquito bite. This is very briefly what the cycle is. So we will need that for the rest of the talk. But now, because we were supposed to be 3 people, then 2, and then finally I am alone in this, I will enlarge a little bit my presentation with some interesting facts about malaria. that in principle do not have anything to see with what we are going to explain later, but which I think they help us to place into context what's this disease. First, Plasmodium is a very ancient organism. Today we can have malaria not only in humans, not only in mammals, but also, for instance, in reptiles. And this gives us an idea that when reptiles appeared on the planet, probably the Plasmodium were already there. And this has been confirmed by looking at the blood samples from mosquitoes that were included in amber from the Jurassic, and dinosaur DNA was found in those mosquitoes. That was a clear confirmation that probably dinosaurs suffered some type of malaria. Talking about humans already, the history of malaria is also very old, and we have mentions of its symptoms, which are this enlarged spleen, because the organism has to get rid of the infected red blood cells, periodic fevers, headache, chills. Those were described in a number of very old documents, like the Evers Papyrus in Egypt, and even before that in Mesopotamia clay library, or before that in a Chinese medical text. And even before that, because nobody knows when the Greek fables appeared, it's supposed, or it's almost sure, that the fable of Hercules and the Hydra is based on malaria, because the Hydra is a monster that lives in swamps, in very humid areas, and from the description that we have in the Greek text, most likely the Hydra refers to malaria. Also, very famous people were killed by the disease. The most well-known probably are Alexander the Great, Genghis Khan, and King Tutankhamun. And actually, malaria was so prominent in ancient Egypt that the people who built the pyramids, they were quite bad smelling. It seems that they had to wrap constantly their bodies in garlic as a repellent of the mosquitoes. This is also a historical fact. And then more recently, the history of, or the stories of malaria are not so interesting or so funny. There were some characters like Julius Wagner Joyrek and Henry Judah Heimlich that performed experiments with malaria parasites that were on the limits of ethics. In the case of Wagner Joyrek, who actually he got a Nobel Prize in Physiology or Medicine for his discovery of the therapeutic value of malaria inoculation to treat some diseases. Actually, what he was doing was to treat neurosyphilis patients, in this case, with malaria parasites. The idea, this was called malariotherapy. Actually, it's a real name for this type of therapy. The idea was that when you infect somebody with malaria, because one of the symptoms is the periodic fever, this increase in temperature, usually, or it can kill some other pathogen. In this case, in a number of people, it killed the pathogen which was causing syphilis. So people, in some cases, did not die of syphilis, but most of them ended up dying of malaria, which I don't know if that was the original idea. This seems to be something from the past, but actually more recently, you might know of a maneuver called Heimlich maneuver. Is when you get a stone stuck on your throat. To remove it, you have to do this type of action on the person. This is Heimlich himself. And actually, he published not so long ago, in 1997, the proposal for malariotherapy for HIV patients. So 20 years ago, still were people publishing in good journals the proposal that infecting people with malaria could be an interesting therapeutic strategy. This is sad, but even, well, we'll see some more sad aspects later on. Chronologically, and again turning to optimistic things related to malaria. Paul Ehrlich was the first one to develop a chemical against, synthetic chemical against the disease, which was methylene blue. They even made a movie about this. Methylene blue was actually called the magic bullet, and the idea was that it could kill very specifically malaria parasites without harming the rest of the tissues in the body. Actually, methylene blue is one of the best anti-malarial drugs that we have still today. It was developed mainly during World War I, when the soldiers were dying in malaria endemic areas. But it was not very favored by the soldiers for aesthetic reasons, actually. One is that it painted the sclera of the eyes blue, so that the white in your eyes was turning blue. And also they noticed that their urine was also blue. And then they didn't like that for some reason, and they, when they were given the pills, they were just throwing them away. So for this apparently innocent reason, methylene blue didn't find its way as a malaria therapy. Something better was quinine. As you know, this is probably it's the best anti-malarial that we have today, with relatively few side effects, but with a good anti-malarial activity, but with relatively serious side effects, like you lose hearing. It has also, it can give you some problem with sight, and that's why it's not used except in very extreme cases. When all other drugs that we have today fail, then we give quinine. Which has also an interesting story. Actually, quinine comes from a place where malaria was not present. It comes from the bark of the cinchona tree, which is a tree growing in the South American forest. And malaria was not known in America until the Spaniards went there. It was a disease exclusive of Africa and Asia, and there was no malaria in South America. But then when the Spaniards arrived and they realized that they were getting malaria, they started trying some of the drugs that the South American people had for when they had fevers for other reasons, and one of them was quinine, which they found it was a very good drug against malaria. The problem with quinine is that those trees are growing really scattered throughout the forest. So one tree is here, the other one is 10 kilometers away, so it was impossible to obtain a large amount of quinine. And its chemical synthesis, it's apparently also very tricky because of this funny ring that it has here. This was almost impossible to synthesize at an affordable cost. Then the chemical industry ended up with chloroquine, which was one of the, after methylene blue, one of the first synthetic antimalarial drugs. As you can see, the structure of chloroquine is very similar to quinine, but with this ring open, and this is much easier to synthesize. Again, the reason, always the advances in malaria, it's sad, but they were because of problems that had nothing to do with people who were suffering from the disease in endemic areas. It was not, methylene blue was not developed because people were dying in Africa. It was developed because soldiers in World War II were dying in the war field. Chloroquine is the same. When in the Pacific War or in the Pacific battles of World War II, the American soldiers started dying by the thousands because of malaria. And then it's when all the chemical industry started working very hard to obtain an antimalarial drug, and that's why chloroquine was finally synthesized. And also probably the best chemical that we ever had is DDT. As you know, it's not killing the parasite, but it's killing the mosquito. Also DDT earned the Nobel Prize to Paul Müller, who discovered it. And unfortunately, the promising DDT era ended up, because it was almost at the point of eradicating malaria. There was a point in the 50s when DDT was about to eradicate the disease, but then it was found, you might have read the book Silent Spring by Rachel Carson. It was found that DDT was accumulating in the environment and it had very serious environmental effects, and then it was banned from its use. And actually at the moment that DDT was prohibited, malaria had a very big resurgence. And these are the two last slides of this historical view on malaria. We go back to sad stories of malaria. In the Second World War, apart from promising outcomes like chloroquine synthesis, there were also both the Germans, but also, as you will see, the Americans. They were again going beyond the limits of ethics to find cures against malaria. In particular, in many concentration camps in Nazi Germany, many of the prisoners were inoculated with plasmodium, and then the chemicals that the Germans were trying to cure malaria were trying on those people for use with the German soldiers in the battles of World War II. This is obviously terrible, and this is Klaus Schilling, who was the principal investigator of this research. And this is Schilling at the Nuremberg trial, and interestingly, some of the comments of the attorneys that were defending Schilling were related to an almost identical experiment that the Americans were doing in a prison called Stateville near Chicago. There they were not inoculating war prisoners, but they were inoculating prisoners that were in jail for whatever minor crime they committed, and the reason was exactly the same. They were inoculating people with plasmodium, and they were trying different drugs on them to see if they can find something for their soldiers. Okay, that's enough for history. Now we go back to research. As I mentioned, nanomedicine, it doesn't have to be necessarily expensive. This is maybe a misconception because of some divulgation news that we have heard about, of books by Isaac Asimov. This is still science fiction. We don't have these nanomachines that can operate on individual cells to cure them, but we have something similar based on polymers and on very simple elements that do exactly this job, that can interact specifically with disease cells and that can inject into them some cure so that we can fight some diseases. So this is true, not in that way. What is also true is that although nanomedicine is not as expensive as it would cost to synthesize these nanomachines, there is still this imbalance in wealth distribution. So even if today we have made efforts and we have reached the point that we can have good nanomedicines to cure malaria, nanomedicines that if they were intended to cure cancer or Alzheimer, I am sure that they would already be in the clinics or undergoing clinical trials, because the pharmaceutical companies can obtain huge benefits if they sell something in Europe or the US. If they have to sell something in Africa, they will not recover that investment, so they don't give money to develop this type of diseases. So this is something we have to fight against. Then, what I mentioned at the beginning, where we started in the group with our research. We came from the nanotechnology field, and then we identified that one of the main needs in malaria is that drug efficacy was very bad. Very bad in the sense that as soon as one of the few drugs that are discovered against malaria is starting being used, it was not used correctly. What I mean is that it needed to be administered in very large amounts. There was a limit. If you don't induce in the person secondary effects, then you give as much as you can and for as long as you can. The consequence was that because those drugs didn't have any special affinity to go to the place where Plasmodium is hiding, namely inside the red blood cell, what happened? That Plasmodium was never killed completely, and then you leave always a few parasites around, and this is the ideal scenario to induce the evolution of resistance in the parasite. So the consequence of administering the drugs like this, just you give the drug and whoever it wants to take it, go on, and then there is always a certain amount that it's at the disposal of the parasite. This is the ideal situation to generate resistance. So what we need to do, not only in malaria, but when using antibiotics or any drug against a parasite, is to give doses as small as possible. First, because in this way you don't induce side effects on the person, but mainly because if you give very small amounts but locally very high, and this can only be achieved if you encapsulate your drug in some type of nanovector, if locally, that means where the parasite is, you are able to give a very high drug dose, that will kill it immediately. And you will leave very few parasites around that could evolve resistance. So the general idea would be to encapsulate, the drug would be the black dots, to encapsulate it in some type of nanovector that will bring it specifically to the target cell, in our case, the malaria-infected red blood cell. Then the first prototype that we suggested, again, let me mention that it was at the beginning when we didn't know the field, and we came also from basic research where there were no limits in what you could imagine or do, as long as it allowed you to publish in good journals, that was okay. Then, because Plasmodium is a very, as I mentioned, very smart parasite, it's not simply hidden inside the red blood cell. It's hidden inside the red blood cell, but inside the vacuole. And inside the vacuole is the parasite itself with its plasma membrane. And inside the parasite there are some interesting organelles that are very specific of Plasmodium, with very interesting metabolic routes that we don't have, that are very good targets for drugs. Then imagine one drug against one of these organelles has to go through 4 membranes: red blood cell, vacuole, Plasmodium plasma membrane, and the membrane of the organelle. This is almost impossible to achieve with just a simple nanovector, and that's why very naively we said, no problem, we will design this super complicated nanovector where you will have a first nanocapsule that will bring a second nanocapsule in the red blood cell cytosol, then this will have another targeting element that will bring the drug inside the vacuole, and so on. Of course, when we went with this idea to a pharma company, when we had the first results, they tapped our shoulders and they told us, okay, go away and come back when you have something that works as well, but 100 times cheaper and 100 times more simple. So that's why we named this in the beginning Russian doll, because there was a nanovector inside another, but of course now we have abandoned a little bit this, forced by the reality of the economic world. But going back to the most simple prototype, which is a liposome, we said, okay, let's do just the first step. Let's just try to bring the drugs inside an infected red blood cell and not inside the most similar cell, which is a non-infected erythrocyte. And then our idea was, let's take a liposome, let's take a targeting element, like for instance an antibody against some specific molecule of the infected red blood cell, and let's load the drug inside and see if we can obtain a good efficacy in this way. The first results were really promising. This is, you will not probably see it from the back of the room. In this field there are like several dozens red blood cells, which are just a homogeneous coat of the microscope slide, And we selected that to show just one plasmodium infected red blood cell, which is indicated by the presence of DNA. As you know, erythrocytes are not nucleated, so any DNA that you will see will tell you where plasmodium is. So here we had a single red blood cell with plasmodium. Our targeting antibody is BM1234, was also recognizing only that cell. That was good. But the critical point was whatever we load in the liposome, in this case was a highly fluorescent molecule called a quantum dot, which gives a lot of fluorescence so that we could see clearly what was going on. The quantum dots that were inside the liposomes were only and exclusively in this one infected red blood cell, and we could not see any quantum dot fluorescence in healthy red blood cells. Then we say, perfect, we had 100% efficacy in both ways, so we could detect all red blood cells. Here I show one, but actually it was 100% of infected red blood cells that we could recognize, and not a single non-infected erythrocyte. We said, perfect, now let's already, we have this magic bullet against malaria. Let's remove the quantum dot, and let's put the drugs, and let's eliminate malaria and eradicate the disease. As you can imagine, when we started trying to load drugs in the liposomes, the results were not so optimistic. We could indeed improve significantly the efficacy of the drugs as compared when they were administered alone in free form, but we were very far from curing the animals in vivo assays. There are a number of reasons for that. That we will see some of them in the next slides, but clearly we were still very far from having a good nanovector. And although we had 100% efficacy in vitro, if we wanted also 100% efficacy in vivo, we needed a number of improvements. Some of them are mentioned here: probably better drugs, better targeting, better encapsulation efficacy, strategies to obtain better efficacy in vivo, probably new targets, as I mentioned, maybe not red blood cells, but we could consider other targets. Oral administration is also very important. And all of these things were not contemplated in this first immunoliposomal prototype. So we started a long path that we are still walking. It is what we call the Lego path, because we had our nanovector, which has essentially three elements: a nanocapsule, a targeting element, and the drug. And then, as you will see, by changing some of these things, we have improved significantly the efficacy of those drugs. And some of those strategies can be of use for you immunologists. The first thing that we could try to improve, in this case liposome or nanovector performance, is combining drugs, not using only one, but several of them. This is already a good strategy for malaria, which is called combination therapy. And actually, the best therapies that we have today against malaria are combination therapies, where two drugs are combined. And these two drugs are affecting different parts in the parasite, and they have different pharmacological characteristics. And actually, precisely because of that, because their pharmacology is different, very usually these drugs that to work well must be in a very precise ratio, like 1:2 or 1:4 or whatever. This equilibrium is quickly lost because they are usually eliminated at very different rates from the organism. As you start with a 2:1 ratio, very quickly after a few hours, probably minutes, you start having a ratio that it's not the right one to work. Then we hypothesized that with our liposome technology, we could probably load different drugs in a single liposomal structure. For instance, our proof of concept was to load a hydrophilic drug in the liposome core, which by definition is hydrophilic, and a hydrophobic drug in the liposomal lipid bilayer, which by definition is hydrophobic. This actually is one of the things that could be, I think, easily exported to vaccination strategies against malaria, because many strategies rely on on a single antigen, or if you want several antigens, you take the whole organism and kill it, and you vaccine with a parasite that it's not active anymore. But probably you could also make use of this and select not only one, but 2, 3, 4, or 5 antigens that could be then loaded in nanocarriers that could present them correctly to the immune cells. And actually that would be much easier to do than what we are trying, because remember, our target are red blood cells, which are absolutely inert bags of hemoglobin. They do nothing but carrying hemoglobin. They've done endocyte. It's very difficult. They have a membrane that is very impermeable to anything that is not oxygen or CO2. And then it has been very tricky to design something that can inject drugs into red blood cells. Then imagine how easy it would be to deliver something to the immune system when you have your phagocytic cells that will devour it immediately. The first strategy that we use for loading huge amounts of hydrophilic drugs in the liposomes was to use a pH gradient. This is a very efficient way to load drugs into a liposome, especially if those drugs have protonable groups. In this situation, if you go through the different pH, you will always have one pH where your drug has no charge. You will always find this. And usually this is around neutral pH. At neutral pH there is a small, even if it's just a small fraction of your drug population that has no charge. Then, if you work at this pH, those pyronidine molecules that have no charge will have affinity for the lipid bilayer, because it likes non-charged molecules. Once they are in the lipid bilayer, they will move around, and we can very easily make liposomes with an internal pH that is acidic in this case. Then, and this can be held in the liposome for hours, even weeks. Then when this drug that is running around the lipid bilayer, at some point it will briefly phase the lumen of the liposome, it will be exposed to a very acidic pH and it will protonate. And once protonated, it will immediately jump off the lipid bilayer towards the center of the liposome. In the end, what you get is like a sponge that is soaking drug like crazy, and then you can get really huge amounts of drug in this type of liposomes. As you can see, the efficiency of encapsulation of pyronidine was extremely good. For weeks, it was no leaking. And drug release was also, once we had the liposomes, it was in storage conditions, it was very stable. To make the long story short, we then chose atovaquone, which was a drug that, when looking at it, it seemed to be quite similar to cholesterol, which is a membrane component, and then we thought that it could enter quite well in the liposome membrane, and it was true. And then we had these nice liposomes with pyronidine and atovaquone. And then, when we tried those so far in vitro assays, we still did not go to in vivos. You'll need to look at the numbers, but I can tell you that the efficacy of these liposomes for the activity of both drugs was very much larger than when both drugs were delivered individually to the cultures. So this seems to work nicely, and now we are thinking of going to in vivo assays with it. Besides this good encapsulation that I just mentioned, what else can we do to improve our liposomes? Maybe a better targeting. I mentioned that we had that very good targeting in vitro experiments. Remember that microscope slide with a single cell that was really good targeted, but the disaster when going to in vivo. Then we suspected that maybe we need much better antibodies to go to in vivo. And those antibodies simply do not exist if we are looking for Plasmodium molecules. I mentioned before, Plasmodium is a very smart parasite. It's not only changing all the proteins that is exposing to the outside of the infected cell, so that it's almost invisible to the immune system. It's not only changing them, but it's exposing very few of them. And actually, when we looked at the antibody that we were using, this BM1234, remember, we found out that most of the antigen, the protein that recognizes this antibody, is intracellular. And only occasionally we could see that this protein probably is exposed to the exterior of the cell. Then we were actually having a very bad antibody, and this can be largely improved. But everything we tried to improve it by looking at new plasmodium-derived antigens was a failure. Plasmodium simply doesn't have reliable antigens exposed to the outside. It doesn't have them. Then the student who was doing that was almost on the verge of suicide because nothing was working. And then we said, okay, let's try just a proof of concept to show that your liposomes work. Let's take an antigen that is in all red blood cells. Okay, we will also target non-infected erythrocytes, but you will for sure target very nicely all the plasmodium-infected erythrocytes. So we took there glycophorin A, which, as you know, is a constituent of the membrane of red blood cells. And here, when we had our liposomes targeted with anti-glycophorin A antibodies, you see the targeted cells were all of them. In comparison, BM1234 was not even visible at this scale. So imagine how bad was our antibody, and probably that's why it works so badly in vivo assays. Then we did all the controls. All the cells were correctly targeted with these liposomes targeted with anti-GPA. Not only that, but again we go back to the economic issue. People who work with cancer or Alzheimer, let's take cancer, and they have a liposome that targets all their cancer cells, they are happy with that. But they don't care if it's only a 1% of the liposomes that target the cells, as long as all the cells are targeted and killed, and they use 99% of liposomes, very expensive, that will never get to the cells, but they don't care because they kill the cells and they can afford paying that. Then with malaria, we cannot afford paying that. With malaria, we have to design nanocarriers that all of them are doing their job. So we cannot make liposomes and pretend that only 1% of the liposome will go to the target cell. 100% of the liposomes have to go to the target cell. And this is what we looked at, and this is what we obtained by working at some precise antibody ratio or antibody abundance on the liposomes, and using the correct binding strategy, we could see that all our liposomes were targeted to our infected red blood cells, which is what we really want. Then, with this new prototype, we had really nice results. When we were using plasmodium antigens, antibodies against plasmodium antigens, because plasmodium doesn't export absolutely anything during the first 24 hours of its intraerythrocytic cycle, only after these 24 hours it starts changing significantly the erythrocyte membrane. And then is when this first antibody that we were using was recognizing something in later stages. That means that you were leaving plasmodium very happy and very quiet for 24 hours, which is a good time. It has built already a significant amount of parasites that are almost about to egress. So if you enter too late in the plasmodium life cycle in the red blood cell, it's no good, because you will probably have little time to kill the parasite. Then with this new strategy, what we obtained inadvertently was that we were also targeting early stages. Just as soon as the parasite enters the red blood cell, we can already target it, because glycophorin A is in all erythrocytes. And this showed in our in vitro assays, when we take chloroquine, one of the first drugs for in vitro testing. Chloroquine is quickly killing all the parasites. When we encapsulate chloroquine in this liposomal prototype, at concentrations where free chloroquine is doing nothing to plasmodium, the same concentrations of encapsulated chloroquine in these nanovectors is killing the parasite very efficiently. Not only in early stages, but also in later stages. Then that gave us the green light to go, as you will see in the next slide, to in vivo testing. But there was another advantage that we did not even suspect at the beginning. All our hypothesis is we are going to build nanovectors that will target specifically the infected cell. That was our ideal scenario, because that is where you have your parasite. Then when we are doing this, of course we kill the parasite in our targeted cells, but if those Plasmodium cells that escape, if they invade the next door red blood cell, they will be again in a safe haven where nothing will be affecting them. With this new approach, if we are loading liposomes targeted with glycophorin A, then to all red blood cells, if we are loading those drugs in all red blood cells, we are placing Plasmodium in a very difficult situation, because as soon as it invades a cell, the drug is already there, and then the viability of the parasite should be very low. It's what we call the Little Red Hood strategy. You enter your home and the wolf is already there. And indeed, in vivo assays this time, yes, we could really eliminate and cure the animals, and no residual parasitemia was left. This, in addition, was done in a mouse model that was humanized, so that those mice had human red blood cells in their blood circulation. It was expensive. Every mouse was 2,000 euros. That's why we had to do this in collaboration with GSK. But the results were really promising. And here we are. I am sure that if you show these results to a pharma company, and this is for cancer, this is already in clinical assays. But GSK itself told us, too expensive. A liposome is too expensive. It's for intravenous administration. Go back to your bench and come back to us when you have something cheaper. Then is when we started working with things other than liposomes. What can be cheaper than a liposome? A polymer. As you know, polymers can be synthesized for ridiculous amounts. And we started working with a type of polymers called polyamidomines that were already very well known in the medical field. They are in principle quite safe, and they have been used to encapsulate different types of drug. Our idea was we will remove, remember the Lego strategy, we remove now the nanocarrier liposome and we place the nanocarrier polymer. But we were considering still that we had to add some type of targeting molecule like an antibody. Well, to our surprise, in the first preliminary assays, where we were just checking, the first control is the polymer or the liposome without any antibody. When we were adding these polymers that can be loaded with drugs to a culture where we had both infected and non-infected red blood cells, oh surprise, you don't see it here, but again, the field contains about 10 or 12 erythrocytes, all of them but one non-infected. And those polymers, without any type of targeting molecule, had a tropism to the infected red blood cells, which was very good. Several polymers do that. We don't know exactly the reason. Probably is some relation with charge or with some particular folding of a part of the polymer. We have seen different polymers doing that, but so far we have not found a unifying trend. That you say, okay, if you have this in the polymer, we'll do that. We don't know why they are doing it. But in this particular case, it was good luck. This is what we call the Trojan horse strategy, because apparently in vitro the cells were not suffering and we had no hemolysis, which very often happen with many other polymers. So apparently the red blood cell was perfectly happy, but Plasmodium, as you will see here, was not so happy when we loaded these polymers with drug. First, we check drug release. It's important that if you have a nanocarrier with a drug, that as soon as it enters the blood circulation, it's not immediately exiting the polymer, because then remember that the Plasmodium life cycle is lasting for 48 hours. Then at least you want your polymer with the drug for about 24 hours around. This is what we observed. We got, in this case, 100% release after 24 hours. And both in vitro and especially in vivo assays, these polyamidamines work quite well. And actually, the 100% viability that you see here is with those two polyaminoamines loaded with different amounts of chloroquine, when the same amount of free chloroquine was not able to cure the animals. Then those were also very promising data with in vivo assays. And here we were always making numbers. It was almost like a frenzy when we had a new prototype. We took paper and let's see how much does it cost. Then the first immunoliposome, if you count the price of the lipids, the antibody, and blah blah blah, we take a common target, which is how much will it cost to reduce tenfold the in vitro efficacy of a drug, in this case chloroquine, in 1 liter of culture, blood, whatever. Then for the immunoliposome, this was an incredible 51 euros. This cannot be used for malaria. In this case, these polyaminoamine-derived polymers, it costed only 40 cents. Now we are getting closer to something that can be useful. And I'm not showing them here, but there is a new type of polymers of dendrimeric nature that we have gone down with them in vitro assays to half a cent, compared with the 51 euros of the immunoliposome. With some of those, we could not go to in vivo assays with animals. And actually, with polyamidamines, although generally, as I mentioned, they are not toxic, we observed that at the amounts that we had to give the animals to cure them, they showed some residual toxicity. So we were not completely happy with them. And we are going now to new types of targeting molecules and of encapsulations. For instance, one of them is considering, instead of synthetic polymers like polyamidamines, that they are after all synthetic, or dendrimers, we are starting to work with natural polymers that, in addition to being usually much cheaper to obtain, they are also very innocuous for the body. And then we are starting to play with chitosan nanoparticles. Chitosan is a well-established encapsulating structure, very safe, very innocuous, and already used in several medical approaches to many diseases. And as targeting molecule, we have started using heparin. Heparin is a polysaccharide that also was observed to have a very specific binding to infected red blood cells. I don't go into the details of how we did that, but by comparing infected with uninfected red blood cells, heparin was a binding that was comparable to that of an antibody, and much cheaper to obtain, and in principle safer, because it doesn't induce, it's an endogenous molecule, it doesn't induce rejection when you treat with heparin. It has other problems, as we will see later. Everything we did had a problem. You always have something that needs more thinking to improve it and to go one step further. In this case, what we were planning to do, here I show one experiment with liposomes, but instead of liposomes, take chitosan. An advantage is that heparin is a highly negatively charged molecule and chitosan has positive charge. And just by mixing them, you have an immediate formation of targeted nanocarriers. But here in this example, we were again using liposomes. And our idea was substituting heparin for the antibodies. And again, our hypothesis was we will get this result, targeting of the drug to the infected cell. And in addition, here we will have another benefit because heparin is also an antimalarial drug. It's a weak antimalarial, but it's working on an interesting stage of the disease that you will see later. And actually what we saw with this strategy was what we hypothesized. This in this case is an antimalarial called primaquine that we selected to have a mild activity. This is 100% viability. And then when we work with a primaquine concentration that kills some parasites, because we needed something like that to see differences, when we encapsulated primaquine in these heparin-targeted liposomes, the activity of primaquine increased significantly. So this is 100% viability. Here we would have 0% viability. And indeed, heparin was acting as a targeting molecule, just as if it were an antibody. And in addition, we observed that it was also acting as an antimalarial agent in itself. Heparin is actually working in a critical step of the malaria life cycle, which is invasion. It binds the merozoite, which is this form of the parasite that is free in the blood again for a few minutes after an infected red blood cell, which is mature and filled with 16 to 20 merozoites, is bursting. Those merozoites, in a matter of 2, 3, 4 minutes, have to invade the new red blood cells, otherwise they will die. At this critical point, heparin, if present, will bind the merozoite and will block invasion. This is the activity of heparin as an antimalarial. And this gives us some interesting properties of interest in immunology that you will see in the next slide. And here comes, as I mentioned, every step forward encounters some obstacle. Heparin is a potent anticoagulant, and then we had to be very careful how much we were using, and actually we were working at concentrations that were quite anticoagulant, and that I don't know if they could be useful for clinical assays. And then here we briefly explored other alternatives. There are many molecules in the nature that are similar to heparin, and many of them are present in marine animals like sponges, sea cucumbers, and algae. And we were also working from our Woods Hole time, we were in contact with groups that were working with these types of marine animals, and then we obtained some polysaccharides similar to heparin from them. And the results were not excellent, but some of them gave promising results, like fucan polysaccharide that had the capacity to eventually cure some animals, although here I think we are still a bit far from the optimal situation. But here comes, I show this because there is an interesting experiment that we were doing here that we observed first with heparin. When we were treating animals with heparin, and those that were cured, because eventually some mice were cured, we did the experiment of reinfecting those cured animals again with Plasmodium and not treating them. And they did never develop the disease. They were resistant to malaria. And the reason for that, this is shown here. An untreated control doesn't have any Plasmodium antibodies against Plasmodium, but actually it doesn't only happen with heparin, but also with many antimalarials. Once you cure the animals, they very often develop resistance. But in the case of heparin, it was very clear, because of this activity of blocking invasion of the merozoite. What we think is happening there is that the merozoite cannot invade the cell, and it's for a much longer time in the blood circulation. Enough time for the immune system to build up an immune response. So this is very good. Heparin might have a triple life, not only a targeting element, also an antimalarial element, and even it could be a type of somehow vaccine adjuvant. But we are again with whatever we develop, now no matter if it's liposomes, polymers, cheap polymers, cheapest polymers. Also with this, when we went again to the pharma industry, they told us, okay, yes, I remember you came 10 years ago with your liposome idea, and I remember I told you, go back and bring me something cheaper. I remember you came with your nice polymers, they were cheaper, and I told you, come with something still cheaper, and now you come with this. That's great. But again, the tap on our shoulder, all these things, they are to be administered to humans, my friend. And then what happens for things that have to be administered to humans? That we need to go through clinical assays. And you know that 15, 20 years of clinical assays are very expensive, and the pharma company will not go through them if they have to recover that investment in Africa. No way, they will never do that. Then that brought us to the last frontier, which is where we are now, and this is maybe a wild idea, but so far it's having some promising results. We said, okay, if we cannot target the human because there are those many problems, why don't we take one of the strategies that Plasmodium, this smart parasite, is using to escape when for instance, you are treating an infected person with anti-malarial drugs. The parasite immediately activates the formation of gametocytes. If you remember, the gametocyte is the form that is taken by the mosquito and that will allow the parasite to continue its life cycle outside of the human. Then very clearly, when it feels threatened in the human, it activates its escape route to the mosquito. And this is an advantage because then it can wait there for a while until it bites another human. Then what happens if we try to kill the malaria parasite in the mosquito? Is that feasible? Does it have any meaning? We don't know, but we are just trying. This will need new nanovectors, and we will probably need new drugs. And luckily, this idea seemed interesting for some funding agencies. We got what we call the Nanophiles project from the European Commission, and the idea is to develop new strategies to administer anti-malarial drugs directly to mosquitoes. So, this is the last slide. My final message would be a little bit that I don't care if we talk of Russian dolls, little red hats, Legos, or Trojan horses or magic bullets. We think that nanomedicine can be an option to treat malaria, and not only malaria, but other diseases of poverty. You just need the funding agencies and the institutes to give space and funds to people who are working on that. And I have to thank all the people who have been passing through the group during these 10 years, and thank you very much for your attention. If there is some question, I can try to answer it.